Okay, if you haven't watched part 1, please go watch that right now because I explain how to implement the Miller-Rabin Primality test, just the Primality test, not how to generate any large primes or whatever. I'm going to do that in this video, so go watch part 1 if you haven't already. I'll put the links in the description. I don't know, should I do the time complexity analysis first, or should I do something else? I feel like I should just show you how to generate large primes. You should never use this in production. I'm just going to restate that. You should never use your own cryptography library when you're writing something that's going to be used in public because it's very insecure, and I already told you. Okay, so don't use this function on your own. Like don't use cryptography stuff that you wrote yourself to make stuff that's going to be used like in projects that other people are going to have to use. So yeah, here we're going to create a function, get prime, and this is going to get, well, okay, I'm going to rename it gen prime. It's more accurate, I guess. Gen prime. This is basically just going to generate a prime with bits number of bits. So the way you usually do this in cryptography is you generate a very large odd number and you check if it's prime. You don't do this by systematically going because, you know, we need to use cryptographic randomness. That's mostly here. So we're going to keep generating large odd numbers until we get a prime one. So here's how we're going to do this. Found, false, well, not found, generate a large prime number with a specified number of bits. So okay, range. How many bits does this actually need? I think it's bits minus 1. I think that's right. And then multiply by 2 plus 1. Okay, hang on. Yes, multiply by 2 and then add 1 to make this odd. So this guarantees that A is odd. And you're not going to be able to see that. Okay, so now we have a large random value of A. We're going to check if it's prime. We're going to turn it. Oh yeah, we don't actually need this. We don't actually need this. We can just do while true. So yeah, if at any point we'll find an actually prime number, then we can return it. Yeah, we just keep going. This is not guaranteed to stop, but the density of primes is there's 1 over log n, I think. Yeah, density of primes is 1 over log n. If n is the number that you're searching around. So if we have bits number of bits, that's going to be 1 over bits. So if bits is like something reasonable, like 1,000 or 2,000 or 4,000, that's probably going to work. And since RSA usually requires primes that are of size like 4,000, 2,000, something like that. Yeah, I'm not a cryptography expert, but it's not something ridiculous like 1 million. It's going to be in the thousands or higher or something. It's not going to be that big. Okay, so this is probably going to stop. So we can first generate a small prime. So let's say it's going to have 10 bits. Okay, we're going to have to print this. So close out that. Oop. Okay, so we're going to print prime 1051. Is this prime? Let's check. Yes, Wolfram Alpha. All right. Yes, it is. What if I use a smaller value, like 6 bits? 89. Yes, we know that's prime. 8 bits, 373. Okay, can't verify it that fast. 6 bits, 83, 67, 73. Yeah, okay. It's generating reasonable values. So what if we like do something ridiculous, like 1024? This is not ridiculous. So we're gonna wait for a while. Okay. So I'm gonna explain why it was slow but a bit fast. I mean, why it didn't take that long. So we're gonna ask if this is prime. maybe Wolfram Alpha can't handle numbers of this size. Okay. Just for this is just for like proof of concept. So let's see. Is this number prime? It is prime. Okay, so let's try another number just to make sure that it actually works. Here, let's go. Copy this number and ask if it's prime. It is prime. Okay, so it looks like our program works. But now we're gonna test for compositeness. So here's what we're gonna do. We're going to generate two prime numbers, P and Q, and then we're gonna multiply them together. This creates a semi-prime. And Wolfram Alpha is gonna have the same algorithm as us. So I mean, that doesn't really matter. We're just gonna test Wolfram Alpha to see, or actually our program, because Wolfram Alpha is like guaranteed correct. We're going to test if our program accurately generates primes. Okay, so this is not a prime number, but it has big prime factors. Bruh, okay, this is... Oh, is there anything? I don't think so. Okay. What the heck? Why doesn't it? This doesn't make any sense. What? Okay, well, we're gonna go with smaller bits because this is just a demonstration. Smaller number of bits. Let's see how this goes. Okay, this is a pretty small number. It's gonna tell us if it's prime. Wait, what? I thought it... Here, let's just ask if it's prime. Because it could handle these. Is not a prime number, right? And that's true because we multiplied two prime numbers to get this number. Yeah, so I'm pretty sure our thing works. I should do a time complexity analysis now. So, no, let's get it out. Oh, okay. Whew. Time complexity analysis is always fun. Okay, so got the drawing tablet and the pen, right? Okay, so okay, OneNote. I'm gonna create a new page, hide the title. Should I go into OneNote mode? I mean, it makes it faster, so I mean not faster, bigger. Let's go to OneNote mode, so you can only see the OneNote screen, the drawing surface. Okay, so time complexity analysis. If we're gonna be first considering top down, so we need k values of a. If k equals 40, I mean, we'll just consider k as a separate variable. So we're gonna do k values of a. So we're gonna do k tests. How much does each test take? Well, we're gonna be going through like the exponents from n minus 1 over 2, n minus 1 over 4, okay, and so on, down to n minus 1 over 2 to the k. And we know this is going to be odd, so we know 2 to the k is less than n minus 1. Oh, well, less than or equal to. Anyway, it's not going to exceed n minus 1, so we can approximate this as k is going to be less than or equal to, oh, I'm reusing a variable k. Ooh. Okay, you know what? I'm just going to say 40. 40 val. You know, that's not accurate either. Okay, you know, I'll just not use k for this. I'll just use something like m. So yeah, okay. So this is all the exponents we're testing. If you remember over here, that's all of these terms. All of these terms over here. We're going to be testing all of these. And how many are there? Well, there's going to be log n, right? So m is less than or equal to log n. So yeah, we know we're going to test log n exponents. So that's another That's another factor to our time complexity. And when we're testing each exponent, we're going to have to calculate. Actually, no, the first calculation is of a to the power of n. Actually, wait, this is conflicting. I hadn't thought about this before. Okay, so the first calculation, we're just gonna have to find. Remember in our script over here, we find the odd factor of n by continually dividing n by 2 until we get to an odd number. So if we have to divide by a lot of 2's, so n minus 1 over 2 to the k. Oh yeah, we divide n minus 1. If this is a small number, that means m is large. And wait. Okay, so okay, never mind. I was confused by something. Not confused by it anymore. Okay, so keep writing k. Okay, so we have to calculate this number, and in order to calculate that, we had to go through log n steps. So we're going to be adding a log n, and that doesn't really do anything because we already have a log n. So that's just going to be a log n plus log n. That doesn't really do anything. Okay, so next thing to know is that for each of these log n exponents, we're going to have to calculate a to the power of exponent mod n. And I should probably research the time complexity of this, but I think it's something like log n because, well, I mean, okay, so this is access to like really low level functions, but so n has log n bits. If you do calculations, you're gonna need something. You're gonna need to calculate a to the 1, a to the 2, a to the 4, a to the 8, and so on up to a to the something, and you're going to need to calculate all of these, and this something is going to be approximately equal to log n. It's going to be proportional. It's actually log base a of n, but that's just log n. When you're analyzing time complexity, like the bases to logs don't really matter because you're just looking for, because linear differences don't matter. So yeah, we're going to need to calculate log n of these exponents. Multiplying them together is also going to take log n. So we're going to be doing for these for each of the log n exponents. So each exponent is probably going to take log n to calculate when we're raising a to the power of it. And this has access to lower level functions, as I said previously. So maybe this is faster than log n. So I don't really know. And I think that's all. I think that's all we have to do. I think. I don't. I'm probably missing something. Let's see. No, I don't think we are. Okay, so multiplying this together, I'll just scroll a bit to the right. Okay, so this is equal to O of k log n, which is just equal to, okay. This is equal to O of k log squared n. And if we're doing something with 1,000 bits or 2,000 bits or something, so we're going to just say 2,000 bits, log n is going to be 2,000, so we're going to get something on the scale of, if k is 40, we're doing 40 rounds. 40 times 4 million. So that's going to be something like 160. Wait, is that right? Yes, 160 million. And this is doable because on a fast enough computer, and if you're not using Python, you'll probably use something like under a second, or like, because from competitive programming, we know that you can do about 100 million operations in under a second or a few seconds. So 160 million should only take a few seconds, and that matches up with what we've seen. So if we do try to generate a 2,000 bit prime, 2048, it'll probably take a few seconds. Maybe more than a few seconds. I don't know, but Python is slow, so Yeah. I think, do we do something that's bad? Okay, what if we do this? Not equal to n minus 1. That might make it faster. Because we know it's eventually going to have to be equal to n minus 1 over 2. Over 2. So why don't we do this left shift 1. Okay, this is taking quite a while. Here, what if I try to use some other library that I've used? So it's called the RSA library. I don't think it's that good. You should probably use a more standard library, but I've installed it just to test out some of these things. Oh, okay, it's done. How long did that take? I actually want to time it now, so you can see because you're watching the video, but I don't know. Oh, okay, it's RSA.prime. Pick prime. Okay, so while we're waiting for that, let's implement the timing. So, yeah, we're gonna have to implement the time library, and yeah, okay. Oh yeah, I should probably use f strings. I mean, I don't have to, but okay. Oh, that thing's done. Well, I think it just does more efficient. I mean, because that library has probably seen the eyes of many more experts. The eyes. What's okay? More experts have seen that than me. So. Than this algorithm. Sorry. So yeah, we're just gonna be waiting around. I'm not gonna cut out this bit because I'm not gonna edit this at all. But yeah, the time complexity analysis says that this should take 160 million operations, and this is slow. Sometimes it might take more, might take less. Oh my god. Okay, I forgot another factor. That's what I was missing. It's not 160 million. It's not that at all. This is just to test one number. 160 million operations to test one number. And we're not going to hit a prime number on our first try. Remember, we're generating random odd numbers. So the density of prime numbers is 1 over log n. And if n, this is just going to be equal to 1 over 2000, for example, if we're generating a 2000-bit prime. So we're going to need to try, we have a 1 in 2000 chance of hitting a prime number for each one that we test. So we're going to need to go through 2000 numbers. And for each one, we're going to need 16 million operations. And this is going to be equal to 160 million. And this is going to be equal to something ridiculous. 320 billion. Okay, that's just impossible. So I think the mistake that I made was with this this log n term, which was the binary exponentiation. It's probably much faster. Should I do a bit of research on the spot? Let's see. Of Python POW function. Okay, it doesn't use exponentiation by squaring. Okay, let's see. O1. What? It's O1? Wait, what? Wait, am I being wrong here? Oh, well, okay, apparently the answer says it's not. Okay, I'm not getting helpful answers here. Here, let's see. That's not helpful. Okay, let's see. Oh, this is C++. Yeah, probably. I don't know. Log B multiplications. Okay, so apparently it is. Okay, that's weird. That's weird. Let's go to other sources. Oh, yikes. Wait, what? Is this... Oh my god. Wait, what? Okay, wait, sorry. We're getting off track. We're getting off track. Okay. Wait, why is it still not done? Wait, what? That previous one finished so much... Oh, is it doing... I think it's the edit I made. It's probably wrong, and I don't want to fix it. So you already know how fast this takes, so you can probably click away. I'm not going to do much else. I'm still wondering about this time complexity though. Like if you're doing 320 billion operations, that should take something like... That should take a very long time. That should take you 1,000 seconds, which is like almost an hour. Oh, okay, it's done already. It didn't print out the time. Oh, okay, it did. Oh my god, this number is much bigger. 25 seconds. Okay. Here, why don't we search up time complexity of Miller-Rabin? Oh yeah, log cubed. Yeah, I thought... Yeah, okay. Was I right? Yeah, k log squared n, and then I got it... Wait, what? Why is it... Wait a minute, what? Wait, hang on, that doesn't make sense. Hang on, that's weird. FFT based multiplication, what's this? I don't think I used that. Because I don't know. Wait, why is this log cubed? That doesn't make sense. Wait, that's weird. Wait, that's super weird. Why? What? Why? Wait, that's a... Wait, I don't understand why it's k log cubed n. Where's the extra factor coming from? Okay, let's rethink this again. There's k values of a. Okay, we already got that. There's log n exponents. Each exponent is calculated in O1 time. This doesn't make any sense. Calculating exponentiation might not be actually O log n. It might be, but I'm not sure. Okay, I'm going to trust Wikipedia here, because I don't actually know where I went wrong with this. That is super strange. Wait, what is this? Okay, something else. K cubed. Okay, Wikipedia could be wrong. Let's try another source. Okay, let's see. It is... Okay, log cubed. Why does it say log n cubed? That doesn't make sense. Okay, maybe multiplying integers, it goes down to log n squared. I think that's what I'm missing. Maybe it's this division part. I don't know. Maybe it's this part that's faster. That's actually log n, but it gets reduced to log. But I didn't consider that it's actually log n. I don't know. Something is weird because I even considered the binary exponentiation. Okay, let me know in the comments where I went wrong. But I do know that's log n cubed, and the reason that it's probably not taking 1,000 seconds is probably because when I do the log n, there's many other factors, so it might not actually be like log base 2. Instead of 2,000, it might be 1,000, or it might be 500 or 200. Because when we're testing a's, we're doing log base a of n, and if a is large enough, it might even be 2 or 1. So yeah, it might not get to 1,000. There might be a few zeros chopped off. That's what makes it faster. So yeah, it runs in about 25 seconds for this test at least. So yeah, that's me explaining the Miller-Rabin Primality test coded up. It's supposed to run in log n cubed. But yeah, it runs faster. So yeah, I just want to reiterate before you leave this video, don't implement your own cryptography libraries. Don't implement your own cryptography functions because it's not going to be secure. It's not going to be as secure as an external library. Like, it might be pretty secure, but like libraries that experts have written are going to be at least as secure as your library. So you might as well use the expert's library, even if you have to learn some documentation. It's worth the sacrifice. I mean, it's not really a sacrifice because it's better for you in the long run, and it should be easier. And you have to, I mean, you're gonna read lots of documentation for other stuff anyway, so it's not that much more. And yeah, security. Make sure you make your apps secure. Don't implement your own cryptography. I'm just reiterating this many times because it's very important. And yeah, that's my explanation. I'll be uploading this code to GitHub. So yeah, I'll be uploading this to GitHub. I'll put the link in the description, and I think that's it. I might be missing something because I missed something in the last video, which was the explanation. So if I'm missing something, let me know. I might do like a video to patch up all those missing parts from these two videos. So I think that's it. I can't remember anything that I'm missing. So thanks for watching. Thank you. Goodbye.